In this video, we're going to look at adding rational expressions. We've already looked at simplifying rational expressions and multiplying rational expressions and dividing rational expressions. Now we're going to add them, and when I say add, I also mean subtract, so we'll also be subtracting rational expressions. Adding and subtracting rational expressions is a good deal more complicated than just the simplifying, multiplying, and dividing ones. And to see that, I want to start with regular fractions, but the basic gist of why they are so much more complicated is rational expressions must have the same denominator in order to add them. If they don't have the same denominator, that means we're going to have to go through a process in order to get their denominators the same so that we then can add them. So I want to look at why this is by just working with some plain fractions. Let's start with 2/5 plus 1/5. Now, I want to talk about how these are actually being represented in reality by using pizza. So basically, the fact that my denominator is a 5 means I have a pizza that's cut into 5 slices. And then to say 2/5 is to say that I have 2 of those slices. The other three were stolen. So I have 2 slices of pizza from a pizza that was originally cut into 5 slices. Then to say 1/5 is to say I have 1 slice of pizza from a pizza that was originally cut into 5 slices. So if I wanted to save space in my refrigerator, I could combine these pizzas into the same box, in which case I would have a total of 3 slices of pizza. They're all still slices that came from a pizza cut into 5 slices. So in terms of doing the math with the fraction, that's saying I have 3/5. So in this, the denominator always stays the same because that's telling us how many are in a whole pizza. How many pieces was the original pizza cut into? We're doing the math with just the numerator, because that is counting the number of pieces we actually have. The denominator is the size of the piece. The numerator is telling us or enumerating how many we actually have. Now let's look at what this means when our denominators are not the same. Let's say we have 5/6 plus 2/15. Now this is saying I have 5 pieces from something originally cut into 6. And I have 2 pieces from something originally cut into 15. So if I combine those into the same pot, I would have 7 pieces, but they're of varying sizes. And so to say I have 7 pieces really doesn't have a lot of meaning attached to it. It's like if I have a bunch of different coins and I tell you I have 15 coins, you don't know how much money I have because the coins are of varying sizes. So what we need to do is go through a process where we essentially relate these to be the same size. And that is a process known as getting a common denominator. In order to get a common denominator, we need to determine what the LCD is. The LCD with these fractions is 30. Now you may just see that, or you may have a process you've already learned to determine that LCD and you know it's 30, or you may not know where I got that from. All of that is okay, but to relate this to the work we're going to be doing with polynomials, I'm going to get this LCD through a process of factoring, because that's how we have to do it with polynomials. We have to factor them to see the pieces of multiplication that's inside of them. So in other words, I'm going to think of 5/6 as 5 over 2 times 3, and I factored the 2 out into prime factors. And I'm going to think of 2/15 as being 2 over 3 times 5 by factoring the 15 into its prime factor so that I can see the pieces of multiplication that's happening inside of them. Now, a process for getting a least common denominator. The least common denominator is the smallest number that all of our denominators divide into. Well, if my denominators have to divide into it, all of them have to divide into it, that means my first denominator has to divide into it. If my first denominator has to divide into it, that means that the LCD has to contain all of the factors of my first denominator. So I know my LCD has to contain 2 times 3, because it has to contain the full denominator. Now it also has to contain the second denominator, if the second denominator is going to divide into it. However, we only need to include the parts that are not already included based on our representation of the first denominator. So in this case, we only need to include the 5, so that gives me my second denominator as a part of my LCD and my first denominator as a part of my LCD, so that both of those numbers are inside of the LCD. In other words, it's okay to, or necessary when determining the LCD, to account for the overlap in factors between the different denominators. So you overlap the factors and only use them once between the factors of the different denominators. Now if I multiply this together, this is going to multiply up to 30. I know for some of you that are pretty skilled at coming up with the LCD with regular numbers, by you kind of just look at it and know it at this point because you've gotten comfortable with the process, this may seem to overly complicate it, but doing it this way through this understanding of factors is how we will have to do it with polynomials. So that's why I'm explaining it this way. So that gives you a sense of what working with rational expressions, adding rational expressions will look like using just numbers. Now we're going to turn to using the ones with variables involved. Alright, let's start with this example 1 here. We're going to start with one where our denominators are the same, just to warm us up to the idea. When the denominators are the same, we do the math with the numerators. So we're going to add those two numerators. Now these two numerators are not like terms, so when we add them, we're just writing them as being added. Negative 2x plus 8. And then that'll be over our common denominator, x minus 4. I want to key you into the directions here. Perform the indicated operation. We've talked about that before, that's just where you have to decide what operation's being asked of you. Here, the indicated operation is addition. The more important thing I want to key you into is and simplify. So once you do the addition, then you need to simplify it. And this goes back to the first thing we covered with rational expressions, simplifying rational expressions. So that's what that's referring to. When we looked at simplifying rational expressions, this is where we talked about we can't cancel terms, so I can't just cancel off those x's. What I have to do is get everything expressed as factors, and if there are any factors that are the same in the numerator and the denominator, then I can cancel those off. With this particular expression, looking at the numerator, a 2 goes into both 2x and an 8, so I'm going to factor that out as a GCF. Also, my number in front, the 2, is negative, and so when I factor the 2, I'm actually going to factor a negative GCF. Doing that gives me a negative 2 times the quantity x minus 4, and that's still over my denominator of x minus 4. Once I have it simplified like that, sometimes it helps students if they have this in parentheses, but basically the entire denominator can be represented as a factor of itself. And then we have the common factor on top and bottom of x minus 4, which means that this expression simplifies to a negative 2. And we're all done with that one. Alright, so for example 2, we're going to look at a more complicated example. We have a little bit more factoring necessary, and we're also looking at subtraction here. So, first of all, I want to address the subtraction issue. Whenever you have subtraction, basically what I'm going to encourage you to do is change that to addition and make the numerator negative. This is changing it to addition of the negative. We've seen this when we've had something like 5 minus 4, and I've said that you can express that as 5 plus a negative 4. So that's what we're doing here. When we're working with rational expressions, it's helpful to associate the negative with the numerator of the fraction being subtracted so that it doesn't get lost in the problem. Time and time again, I see if students don't do this, they lose the negative or don't distribute it properly when necessary. So after changing it to plus the negative of our fraction, what we want to do is get a common denominator to determine the LCD. But in order to determine the LCD, we need to be able to see the factors of our denominator, because the LCD is based on the factors of the denominator. So we need to now factor both of those denominators. The first denominator factors as 5x plus 2 times x plus 2. And the second denominator factors as x minus 3, x plus 2. Now that we have the denominators factored, we need to determine the LCD. The LCD needs to contain all of both denominators, but I always like to start by just saying if it has to contain all of both denominators, I'll just say it's all of the first denominator for starters. So we write out all of the factors of the first denominator as a part of our LCD. Then we also need to include all of the second denominator as a part of our LCD. However, we already have the x plus 2 included, so we don't need to count it again. In other words, in order to get a complete LCD, we only need to multiply in the factor x minus 3. So our LCD is the quantity 5x plus 2 times the quantity x plus 2 times the quantity x minus 3. Now that we have our LCD, what we need to do is rewrite each of our fractions so that they have the least common denominator as their denominator. So I'm going to start by writing down my first fraction. And it needs all of the LCD. So the part of the LCD that it's missing is the x minus 3. So I'm going to multiply in the x minus 3 to the denominator, so I have my LCD. But I also have to multiply that into the numerator. Basically what I'm doing is multiplying in a 1, so these would cancel back out if we were simplifying. We're not going to cancel them back out, but basically we're not changing the value of this fraction, we're only unsimplifying it in order to get a least common denominator. Or we're multiplying it by a complicated 1. Multiplying by 1 doesn't change anything. Now we're going to go through the same process with the second fraction. So I write my fraction down, and then I look at my LCD and I ask myself, what part of this LCD is this fraction missing? Well, this fraction is missing the 5x plus 2. So I'm going to multiply in 5x plus 2. But what I multiply on the bottom, I have to match on the top, so that divides out to be a 1. Once I get my denominators the same, I'm ready to do the actual addition. Now the way this works, as we saw with just numbers, is we do the math with the numerator. So we're going to add those two. However, the result of adding the numerators is just written over one common denominator. So when I do that, it looks like this. So the numerator is added together over one common denominator. Now before we go on, I want to caution you to not do something that is all too common. Once we get it written out like this, when you write it like this, it looks like I could cancel this x minus 3 with this x minus 3. And it looks like I could cancel this 5x plus 2 with this 5x plus 2. You do not want to do this type of cancellation. You cannot do this type of cancellation. While the denominator is in factored form, the numerator is actually being expressed as two very complicated terms. It's this term plus this term. And remember, I can't cancel a term or any part of a term. So when I cancel or attempt to cancel the x minus 3's, while I'm canceling a factor in the denominator, I'm canceling a part of a term in the numerator, and you cannot do that. What we need to do instead in order to simplify this problem is we need to multiply out the numerator. We're going to leave the denominator factored because we like factored form, but we need to multiply out this binomial times a binomial. We need to multiply out this multiplication by distributing the -6. And once we get everything multiplied out, we're going to need to combine like terms and refactor. Alright, so I cleared out the work I had so far to give myself some room for this simplifying work. So I'm going to start by multiplying these two binomials out. That gives me x squared minus 3x plus 3x minus 9. And then I'm going to multiply the other term out. That gives me minus 30x minus 12. I do want to make a quick side note here. Notice that when I distributed this -6, the negative was distributing with it. But originally that negative was the minus that I changed in the beginning to associate it with the -6. This is where that problem usually occurs, that if you don't do that in the first step, then the negative doesn't get distributed throughout the second factor when you're multiplying in this step. Now what I'm going to do is write all of this over my LCD still. Now that I have my numerator multiplied all out, I can combine like terms. And that'll give me x squared minus 30x minus 21. You can take a second to double check me on my math there. But then I'm just going to write that over my LCD. Alright, so now what I need to do is look at this numerator that's simplified down. In order to attempt to simplify, I need to see about factoring it. Now when I look at factoring that, I'm basically, since my number in front of x squared is a 1, I'm looking at factors of -21 that multiply to -21 and that they add to give me a -30. Those two there's no two factors that exist that do that. So we can conclude that this does not factor and be done with it as it is. However, you have to check to see if it factors, because oftentimes it will factor, and then you have to cancel out any factors that both the numerator and denominator share. So with that, we can be done with this problem, and this is our final answer here. So that's the idea of adding and subtracting rational expressions. It's a very involved process, one of the longer ones we will do in this course, but it uses a lot of pieces that we've previously covered and just dumps them all into the same problem. Be patient with yourself as you're working through these. It's more important that you understand the steps and the need for the individual steps. If you make small errors here and there, be gentle with yourself about that. So go ahead and give some of these a try and see how it's working out for you.